Hello everyone, welcome to topic 7.8, representations of equilibrium. By the end of this, you should be able to represent a system undergoing a reversible reaction with a particle model. We will also, or particulate model, we'll also look at how this ties into graphs. So, just as we have seen in the previous units, we can model the reaction to show the relative numbers of particles before and after equilibrium. And we can deduce the value of the equilibrium constant from that. Consider the set of images for this reaction. The system is initially at equilibrium, shown in the first image, and then some AB3 is added, that is shown in the second image. Then the reaction moves to a new equilibrium state, shown in the farthest right. With all the modeling, be sure to consider the states of matter, relative amounts of the particles, the changes to the size of the container, the particles that might react with one another, and so on. Okay, it is also very helpful to make sure you have a key that is obvious. We can also use the information provided to graph changes. Typically, this shows us the change in concentration with time. The reaction above could be shown graphically like this. So where we have our A2, and then this is where the stressor is introduced, and we see it reach a new equilibrium state for both A2 and B2. For the one that's added, we see a high spike, like a straight up spike, because you add an amount all at once, and then it comes back down to reach a new equilibrium. Okay, notice the graphs that change, the changes on the graphs are related to the mole ratio in the chemical reaction, okay, which we went over in a previous section as well. If the system involves gases and change to volume occurs, then all the gases will show the initial change to the conditions. The same is true for dilutions for an aqueous system, okay, so they'll all have that sharp spike or drop. Like there'll be a vertical line. So let's look at some examples. So considering the reaction N2 plus 3H2 yields 2 NH3, given 6 moles of nitrogen, 6 moles of hydrogen, and 6 moles of ammonia at equilibrium in a 2-liter container, draw a possible equilibrium showing how the number of reactants and products might change if the volume of the container was reduced to 1 liter. The drawing is given to you. Okay, so you need to make sure might, so this is a correct relevant change. Okay, so if we reduce this, okay, what happens for gases is when we reduce the volume, they are going to want to shift to the side with fewer moles of gas. So we see we have gas here and gas here. Stoichiometrically, that's 1 plus 3, which is 4 moles of gas on this side, to compare to the 2 moles, and it's a mole ratio. 2 moles of gas on this side. So when we reduce the volume, it needs to adjust how many bodies or like particles, individual molecules are in there. And so it'll shift to the side with fewer. So in this case, it shifts to NH3. So when we count here, we see we have 6 moles N2, 6 moles H2. And if we count, there's 6 of each one. So that was nice that they made it match and mirror. So then when we go over to the other side, we should see an increase in the amount of ammonia, which 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 moles of ammonia, which it is increasing. We should also see that N2 and H2 decrease by close to the same mole ratio. So we count N2, 1, 2, 3, 4, 5. And then we count H2, 1, 2, 3. Okay, so this drawing should show a shift towards the products. Because of the decrease in volume, it needs to shift towards the side with fewer stoichiometric moles of gas. So we look at the coefficients for the gases, the side with the fewest number, it shifts towards. Now, if we were to increase the volume, it'd shift the other way because it now has more space to fluff out. Okay. Considering the same reaction, sketch a graph showing how the amount of reactants and products change if the volume of the container was reduced to 1 liter. So we're going to try and keep it the same, where we see ammonia increasing. We see hydrogen gas decreasing quite a bit. And we see nitrogen gas decreasing, but not by so much. Okay. And because there are no measurements for lines, you don't have to try and make it super stoichiometrically relevant. But since there is a big difference between H2 and NH3 and N2, like N2 specifically, the size in the change, it should be reflected. So that concludes the 7.8 notes. Please complete the you-dos, check your work, and thank you for tuning in.